Hi everyone, welcome back to the course on measurement and instrumentation, and this is our 6th week of discussion, and we are discussing our second module about analog meters. And in the previous class actually we have finished our discussion on analog meters, which is used to measure mostly current and voltages, but that are based on various principles. And we planned we will discuss about different ways, at least using these meters to measure certain physical parameters or physical quantities, including say resistance, for example, phase, power, energy, those things. Okay, so let us try to extend our discussion to the measurement of resistance in this particular class. Measurement of resistance is of utmost importance for various application, okay, be it in the laboratory, be it in the industry. Okay, measurement of resistance plays a very crucial role. Okay, given you have a voltmeter and ammeter, okay, how you will measure a resistance. Okay, so we'll first start with that and we'll see some advanced technique to measure the resistances. Okay, so let's consider that we have simple resistance. Okay, this is say R unknown, this value I am not aware of. Okay, now I want to measure the resistance of this. Okay, this is connected in certain circuit. Okay, to measure the resistance, what I can do is I have to first find out the current that is flowing through this unknown resistor. Okay, and if I know the current whatever is flowing through this, okay, and if I know what is the potential drop across this, okay, so say this is say voltage drop across this resistor, okay, unknown resistor, and if I know say this voltage drop is known, okay, very accurately. Please note that we are discussing this measurement of resistance specifically because we want the measurement to be very accurate. Okay, so say voltage is known, okay, and in the same way I have known to say very accurate value. What I mean by accuracy here, we will discuss this later in this course. Okay, now I have a current which is again known value, again a very accurate value. Okay, so if I have this voltage and current, this current flowing through this resistance and the voltage drop across this resistance, if I have these two values known to a very accurate values, okay, I can say that R unknown is equal to V known divided by I known. Fine. However, the measurement of this current and the voltage across this resistance is a bit tricky. Okay, so we will discuss that why I am saying that this measurement of current and voltage across this unknown resistance is little tricky, rather than there is no I can say a straightforward method to find this voltage and current correctly at the same time. Okay, so let's discuss this particular problem in today's class. Okay, that how to measure this resistance accurately. Okay, but before we actually go into the measurement of resistance, we have to first classify these resistances. We cannot say a resistance of copper and a resistance of a dielectric material, or we cannot measure both by the same technique. Okay, we have to develop or we have to make arrangement in such a way that for low resistance measurement we have a technique which measure this low resistance to a very accurate value. Similarly, for high value of resistance, like for a dielectric material, if I want to measure that kind of resistance, we have to have a different kind of arrangement so that the accuracy is preserved in both the cases. Okay, therefore we have to classify the resistances based on its absolute values. Okay, so the classification of these resistances from the viewpoint of measurement is like low resistance, medium resistance and high resistance. Okay, as per the textbooks, when I say low resistance, all resistance of the order of 1 ohm and less may be classified as low resistance, and in our course also we will stick with this particular definition of low resistance. Okay. So, all resistances of the order of 1 ohm or less than that, like certain milli ohm or some micro ohm, that kind of values, we are saying that they are low resistance values. Okay. When I say medium resistance, usually what we are going to consider in this course is anything like 1 ohm to 0.1 mega ohm or so, but this definition is very vague, and I am not telling that, say, if it is say 1.1 ohm, you cannot use the method that you are using for low resistance. These definitions are not very strict, I would rather say. Okay. So, low resistance, all resistance of the order of 1 ohm and less. Okay. Then medium resistance, I am classifying it in the range of, say, 1 ohm to 0.1 mega ohm. Okay. And high resistance is actually something which can be distinguished from low and medium resistances based on its value, and anything which is in certain mega ohm, like anything beyond 0.1 mega ohm, we are considering them as high resistance method. Again, so if something is, say, 0.11 mega ohm, you cannot say that the method that I am using for medium resistance measurement cannot be extended to it. It can be extended, but if you use a high resistance methodology there, or the technique that we use for measuring high resistance, that will give you more accurate result as compared to the other technique. Okay. So, accordingly, actually whatever we have seen, low resistance, medium resistance and high resistance, accordingly we will also divide our measurement techniques. Okay. So, if I say low resistance, which is of course less than ohm, okay, there are various cases in practical scenario where we have this less than 1 ohm conditions. Okay, like say winding, copper winding of a generator, of a transformer, of a motor, or say earth ground conductor resistance, they are of the order of these values. Okay, if you talk about the modern technologies, if you have, say, very thin pure platinum or say palladium kind of material, and you are trying to have its very thin wire kind of structure at nano regime, you will have this kind of resistances. Okay. So, these resistances are not only useful for electrical devices, but it is equally importance, they are equally important for the electronic devices and electronic applications, including application of modern sensors, IoT devices and so on. Okay. So, low resistance measurement is very crucial. Okay. Medium resistances, we all come across this 1 ohm to 100 kilo ohm resistances in our laboratories, be it common resistors that are available in the lab, PCB traces, all these things are medium resistances. And when I talk about high resistances, which is of course greater than 0.1 mega ohm, you have insulation resistance mostly of motor winding, say generator winding, insulation resistance of the transformers, insulation resistance of electrical cables and so on. Okay. So, all these places you have to measure the high resistance values of these insulators. Okay. So, for these applications also equally important is to measure the high resistance of this insulating material. Okay. So, there are various ways of measuring all these things, but what we will do is we will try to start with the commonly available resistors that we encounter in our laboratories, like the resistances of medium range, or resistances of the order of, say, 1 ohm to 100 kilo ohm, which is more practical. Okay, we all have come across all these resistors. Okay, so there are various methods to measure these medium resistances in the laboratory. Okay, the first is the Ammeter-voltmeter method. Okay, then we have a substitution method. We have Wheatstone bridge method, and then we have ohm meter method. Okay, what we will do is we will discuss some of these techniques to measure this medium resistance. Okay, and once we have the foundation for medium resistance, we will go ahead to measure low resistance as well as to measure the high resistance values. Okay, so the most common way is the Ammeter-voltmeter. If we understand Ammeter-voltmeter method, it will also help us in understanding our first slide, where I talked about a simple resistor, unknown resistor, across which we had a voltage drop and a current flowing through the resistor, which I told that they are known value, but I mentioned that they are sometimes they are not the measurements of this voltage and current are not that accurate, and that's why usually this method may fail for accurate measurement. Okay, so let's try to see this ammeter-voltmeter methodology for measurement of this medium resistance. Okay, so the resistance under test is determined using Ohm's law, where resistance is equal to the voltage divided by the current that we have just seen. Okay, the voltmeter measures the voltage across the unknown resistance, and the ammeter of course measure the current flowing through it. Okay, we can have two different type of connections for this ammeter-voltmeter method. Okay, and you can understand that this kind of arrangement any layman person will try when they try to measure the resistance of any unknown value. Okay, so these are two different combination that I am talking about. I am calling this connection type 1. Okay, this I am calling say connection 1, all right, and this is connection 2. Okay, so whenever I call a connection 1, please remember what I am trying to say is this ammeter is connected in series with this resistance, and after that you have this voltmeter. Okay, so you have current flowing through, the same current actually flowing through this ammeter and the unknown resistance that is under measurement. Okay, also this voltage drop in this case, if you note, is actually the voltage dropped across this resistor R and voltage dropped across this ammeter. Okay, in connection 2, what I have done is I have moved this voltmeter beyond this ammeter, and now this ammeter has came to this side. All right, now I cannot say that current I which is flowing through this ammeter is same as the current which is flowing in the unknown resistance that I have told in this condition. Okay, in this case what I told is the current that is flowing through this ammeter, exactly it is the same current that is flowing through this unknown resistor, but in this case it is not, because the current that this ammeter sees, this current I, is actually getting divided into two different currents. Okay, maybe very small, but voltmeter there is certain current. Okay, and rest of the current is flowing through this resistor. All right, so you have, and please note that these connections are as per the rule and regulations of basic circuit theory, where I have connected this ammeter in series with the resistor, and the voltmeter is connected in parallel which across the component across which I want to measure the voltage. Okay, now the measuring resistance I am calling Rm is calculated as the ratio of voltmeter reading to ammeter reading. Okay, please note that I am using a term Rm and I am not using the term R here. R here, this R is basically my unknown resistor. Okay, this R is the unknown resistor. All right, and what I am telling you that the measuring resistance Rm is calculated as ratio of voltmeter reading, or I am right now I am using the word V, okay, to the ammeter reading, which is reading some value, say I am calling it say V voltmeter and this I ammeter. Okay, now one thing is sure that this Rm is not equal to R. Okay, this is for sure, because we have just seen that there is certain voltage drop across ammeter, as well as this voltmeter is also drawing some current in connection 1 and in connection 2. In both the cases actually this thing is not getting satisfied. Okay, now the measured resistance Rm will be equal to the true resistance R only when the ammeter has a zero resistance. Rm will be equal to the true resistance R when the ammeter will have a zero resistance. Okay, and the voltmeter has infinite resistance. Why I am telling this? Because say this current I is flowing through this ammeter, okay, and definitely if this ammeter which we know that has very small resistance, okay, say this Rm meter is very small as compared to the R value, okay, then also there will be a voltage drop across this. So, if VA is the voltage drop across this, okay, and this, if the resistance is Rm meter, okay, the voltage drop VA will be equal to I into Rm meter, right? Right. So, this voltmeter, whatever it is measuring, is not only this VR, which is the voltage across this resistance R, but also the voltage drop across this ammeter. Okay. So, this V is equal to, basically is equal to VR plus VA, all right. Now, say if my ammeter is a true or a ideal ammeter and it has a zero resistance, means I can simply replace this ammeter by a short circuit, right, and there is no drop or there is no further drop of any potential across this ammeter. Okay. So, the whole voltage is getting dropped across this unknown resistor, okay, and the V is equal to VR because the VA value is 0. So, under the condition when VA is equal to 0, okay, V is equal to VR. Fine. Similarly, consider this case, okay, I have a current I flowing through this ammeter and I mentioned that this current I is actually not equal to IR because this current I is getting distributed into two different currents. One is drawn by the voltmeter, okay. We all know that the voltmeter has usually very high resistances, okay, and this is the low resistance path. So, most of the current will flow through this. However, little bit current is drawn by the voltmeter, all right. So, this current I which is flowing through this ammeter, so I am calling this I ammeter, okay, this is equal to the current IR plus current IV, all right. So, I ammeter is equal to IR plus IV. Now, if voltmeter has infinite resistance, means that I can replace this voltmeter with a open circuit, okay, and in that case there is no IV component. Since it is open circuit, voltmeter is drawing no current, okay. When it is not drawing any current, means this complete I ammeter or this current which is flowing through this ammeter is equal to the current through this unknown resistor or which is IR, all right. So, the measured resistance Rm will be equal to the true resistance R, okay, which we have seen it is not, okay, but this can be equated under the condition that the ammeter has zero resistance while the voltmeter possesses a infinite resistance. However, in practical scenario, you cannot consider that ammeter will not have any resistance. It will have less resistance, but it cannot be 0, okay. As well as you cannot imagine that voltmeter is having infinite resistance or very, very high resistance. It will have finite resistance, it may be very high, all right. So, both the conditions are actually not correct, okay. Therefore, we have to see in practical scenario how to measure the current values or the resistance value from whatever measurement setup we have, okay. So, now consider this first condition when you have ammeter connected in series with this resistor and you have this voltmeter connected, okay. The circuit consists of an unknown resistor, okay, ammeter and a voltmeter connected to a DC source, and say this is the DC source, okay. Voltmeter does not measure the true voltage across the resistor as we have discussed, because this voltmeter is measuring the voltage across ammeter and the resistor, okay. The voltmeter indicates the sum of the voltage across the ammeter and the unknown resistor that we have just seen, okay. So, let us consider the ammeter resistance as RA, okay. So, if RA is the resistance of the ammeter, okay, voltage across it will be IRA, okay. So, VA is equal to IRA, okay, because same current I is flowing in this circuit, okay. Now, the measured value of resistance I am calling, say this is RM1, okay. RM1, because this we are discussing in the connection 1, okay, this was my connection 1. So, I am calling this RM1, okay. RM1 is equal to V by I, okay, and V now is not the actual VR, but it is VR plus VA, okay, and which is divided by current I, okay. VR is equal to I into R. So, this is I into R plus I into RA, okay. Now, divided by I. So, RM is equal to, or RM1 is equal to R, which is the unknown resistance, okay, unknown resistance, plus this ammeter resistance, okay. RM1 is equal to R plus RA. Now, if I want to calculate the true value of resistance, now I have an equation which says that this RM1 is equal to R plus RA, but we are interested in finding R because this was our original unknown resistance, okay. So, R can be simply calculated by subtracting the ammeter resistance from the measured value, okay. The measured value from this circuit condition or this connection 1 is RM1. So, the true value of resistance is equal to RM1 minus RA, or I can say RM1 minus RA by RM1, okay. Thus, the measured value of resistance is higher than the true value, okay. This is the correct statement, right. It is also clear from this equation that the true value is equal to measured value only if the ammeter resistance RA, the RA value is 0, that we have also seen in our previous discussion, okay. Now, relative error in this case can be written as RM1 minus unknown resistance divided by R, or you can also represent it in percentage, okay. So, the measurement error becomes small when the resistance under measurement is much larger than the internal resistance of the ammeter as per this equation, okay. So, this arrangement or the connection 1 arrangement is suitable for measuring high resistance values only, because in the high resistance value measurement only this will have minimal error. Please note that when I am using the term high resistance, I am talking about the higher side of resistance in the medium range only, okay. So, in the medium range only, let me clarify that we have a range of say 1 ohm to 100 kilo ohm, okay. So, if I divide this spectra of resistance, I will have a range of spectra in the medium resistance only, okay, because this is covering a large range of resistance. So, I can have a range of resistance, say certain value of say 1 ohm to say 1 kilo ohm, or say 100 ohm, okay, or say 500 ohm, okay, or say 0.5 kilo ohm, and then from 100 ohm to say 5 kilo ohm, and then 5 kilo ohm to say 100 kilo ohm, okay. So, in the medium resistance also I have a huge spectra, because I am covering a actually very large range of resistance from 1 ohm to 100 kilo ohm. So, when I say this circuit, the connection 1 is suitable for measuring high resistance value, what I mean to say higher resistance in this medium resistance range, okay, means that anything like above 5 kilo ohm, that kind of resistance I am talking about, fine. Now, let us see the second arrangement or the connection 2. So, this was our connection 2, okay. In the connection 2, what I have done is, since I was facing that the voltage that I was measuring was actually the volt in the connection 1, what we have seen is the voltage that voltmeter was measuring was not accurate. It was actually voltage of the voltage drop across the unknown resistor plus the voltage drop across the ammeter, okay. So, the idea is, let us bring this voltmeter near to the unknown resistor so that it measures the accurate value, okay. But does this solve the problem, okay. So, if you see this connection 2, okay, voltmeter is near to this resistor, okay, and In this case, this voltmeter is measuring the true value of the voltage, okay, true value of the voltage which is say dropped across this unknown resistor, okay. However, if you see, the ammeter is not measuring the correct value, because this ammeter is measuring a current, I am calling this say I, okay, which is the sum of current which is flowing through this resistance, and say this I am calling say this IR and IV, okay. So, this I or say I ammeter is getting divided into IV and IR. So, I ammeter is actually measuring IV plus IR, and I ammeter is not equal to this IR value, okay. They are different because I ammeter has two components, this IV and IR. Fine. Now, voltmeter is measuring the correct value, but not the ammeter. Say let RV be the resistance of the voltmeter, okay. RV is the resistance of the voltmeter. Now, current which is drawn by this voltmeter is actually IV is equal to V by RV, okay, V by RV, okay, where RV is the resistance of the voltmeter, and we know that resistance of the voltmeter are usually very high. So, RV is representing a very high value, okay, means that the current that is drawn by the voltmeter is very low, okay. So, now the measured value of resistance in this case, say this is connection 2, so I am calling this RM2, okay. The measured value can again be calculated using the Ohm's law, which is V by I, the voltage dropped divided by I. So, the RM2 value will be equal to V, because voltmeter is representing the correct value, V by IR plus IV, okay. V by IR plus IV, or V by, if I just write the values of IR and IV. IR is the current that is flowing in this unknown resistor, okay, means that V by R, okay, and IV is a voltage, or IV is the current which is flowing in this voltmeter. So, the voltage V, this voltage divided by RV, fine. So, I have RM2 as R by 1 plus R by RV, alright. So, if I have to find the unknown resistor, okay, or the true value of the resistor, I have to rearrange this expression, okay, and R will be equal to RM2, which is the measured value of resistance, into RV divided by RM2 minus RV, okay. Or if I simplify this further, I can write RM2 into 1 by 1 minus RM2 by RV, okay. So, it is very clear from this expression that the true value of resistance is equal to the measured value only if the resistance of voltmeter is infinite, right, when this term is infinite, okay. However, if the resistance of the voltmeter is very large as compared to the resistance under measurement, which is RM2, or you can say RV is much larger than RM2, RM2 by RV will be very, very small, okay. So, because we have already seen that the resistance of voltmeter are usually very high, okay. In most practical sense, this is the case, okay. RM2 value is much smaller as compared to the voltmeter resistance RV, okay. So, RM2 by RV is much smaller value, okay. This value is much smaller, and therefore, this expression that we have just seen, R equal to RM2 into 1 by 1 minus RM2 by RV, can be written as R equal to RM2 into 1 plus RM2 by RV, okay. We can write, and this expression is the value of the unknown resistor in terms of the measured value and the voltmeter value. So, once you know this voltmeter resistance, you can calculate the unknown resistance, and this value is in line with whatever we have seen in case of connection 1, alright. So, the measured value of resistance is smaller than the true value in this case, or the relative error if I have to find, it will be equal to again RM2 minus R by the unknown resistor R, and again I can express this in terms of certain percentage, okay. The measured resistance value RM2 is approximately equal to the true resistor, and we have seen the true resistor value is equal to RM2 into 1 plus RM2 by RV, and if we solve these equations, the relative error value is equal to minus R by RV. Okay, or if I have to consider the mod or the only the absolute value, I can say that the relative error is equal to R by RV. Now, the error in the measurement would be small if the value of resistance under the measurement is very small as compared to the resistance of the voltmeter. Hence, this kind of connection or the connection 2 should be used when measuring the low resistance value, and again the low resistance values I want to say is the lower value of the medium resistance spectra, okay, that we have just discussed some time back. Okay, fine. So, the ammeter-voltmeter method is simple to use, but provide only the approximate resistance measurement, and it is not as accurate as you want. Okay, the accuracy of this method is limited by the accuracy and internal resistances of the ammeter and the external voltmeter that you are using. Okay. So, the ammeter-voltmeter method as I have mentioned is simple and easy to implement for resistance measurement. Again, not for the accurate measurement, but for the rough measurement you can use it. Okay. Of course, it is less accurate. We will see some more accurate measurement methodology for measuring this medium resistance ranges. Okay. The measurement is affected by the internal resistance and accuracy of these meters, external analog meters like voltmeter and ammeter that we are using. Okay. But then there is a confusion that for certain amount of resistance, which kind of connection we have to prefer. For what resistance this connection 1 will be preferred, and of course, we have seen this for high and low values, but this high and low resistances that we have discussed, we have not segregated. Okay. So, the division point between the two methods is at the resistance for which the relative error given by the two methods are equal. Okay. So, for that what we have to do is we have to equate the relative errors for the two cases, and they can be simply equated as RA by R in the first case and let it be equal to R by RV in the second case. Okay. So, if I have to find the value of unknown resistance R, it will be equal to under root RV into RA, and this is the resistor or the crossover resistor. Okay. So, for high resistance values, the first ammeter-voltmeter method is preferred to minimize measurement error, and for lower resistance value, the second ammeter-voltmeter method or this connection 2 gives more accurate result and should be used. And for reference, the resistance that I have calculated just now, this unknown resistance RV into RA under root, this can be used as a reference for talking about say high resistance and low resistance. Okay. So, you can take this as a reference for high and low values. Alright. So, this is about the ammeter-voltmeter methodology to measure the medium resistance. We have another method which is the substitution method. Okay. And then we have Wheatstone bridge method and all. Okay. So, let us quickly see the substitution method at least. Okay. So, consider this arrangement of resistor. Okay. So, I have this unknown resistor R, okay, and this S is a standard variable resistor. So, this I am putting this sign, this S is a standard variable resistor, and A is the ammeter and R is the regulating resistance, and this is the battery which has a fixed potential. Okay. Now, there is a switch here. Okay. Please note that one, let me represent 1 by dots. Okay. This is a dotted line. It shows that it can, this ammeter can be connected to this 2 point. I am calling this point 1 and I am calling this point 2. Okay. So, this point 1 is, if I am connecting this switch to point 1 means now this resistor, unknown resistor is connected, and I can move this pulley or switch to this point 2. Okay. And this is called position 2, means that this standard variable resistance is now connected. Okay. So, both cannot be connected at once. Okay. So, it is connected once to this and then to this, and we will see what this means and why we are doing all these things, all these exercises. Okay. So, R is the unknown resistance that we want to measure, and S is the standard variable resistor. A is the ammeter, and R is the regulating resistance. Okay. Now there is a switch for putting R and S into the circuit, and this is done alternatively. Okay. So first you put S and then you put R. Okay. Let's see how we do. Okay. Now the switch is put at position P1 and resistance R is connected in the circuit. Okay. And the regulating resistance R is adjusted till the ammeter pointer is at a chosen scale mark. Okay. So I have connected this point. Okay. And I have tuned this R value, this small R value, okay, in such a way that this ammeter is pointing to say 3 amp, okay, 3.00 amp, all right, or say 2 amp, depending on what I want. Okay. Now what I will do is I will just change this value to this. Okay. I have now moved this switch to this position. Okay. And now this R is disconnected. Okay. And of course there is a change in current, and say the change in current is like earlier I had fixed it to 3 amp and now it has moved to say 1.2 amp. Okay. Now this S is a variable resistor. Okay. What I will do is I will change this S value to bring this current value from 1.2 amp to 3 amp. Okay. Since this is a standard variable resistor, I will be able to tune the current flowing through this from 1.2 amp to 3 amp by simply changing the resistance of this standard variable resistor. Okay. Now replacing one resistor with another does not change the current in the circuit. Since the battery voltage and the position of R remain unchanged, the two resistances are equal, and that's how the accurate value of the unknown resistor R can be found by equating it to the standard resistor that result in the same current in the circuit. All right. And this method is much accurate as compared to the ammeter-voltmeter method that we have seen. Okay. However, the accuracy of this method is affected if there is any change in the battery EMF during the time and readings on the two settings. And this is the same drawback for potentiometer kind of arrangement. If there is any change in the EMF of the battery, your potentiometer may also result in the erroneous result. Okay. So this substitution method is more reliable, but again it rely upon the battery EMF conditions. Okay. So then we have another method which is Wheatstone bridge method. Okay. Why we are discussing all these methods? Because we want a more refined way of measurement, or we want a more accurate way for measurement of the resistance. Okay. Now this Wheatstone bridge configuration we all have studied at some point, okay, is a very important arrangement used in the measurement of medium resistance. Okay. The Wheatstone bridge, we can say that it's a kind of instrument for making comparative measurements and operation upon a null indication principle. Okay. So you can say that when the bridge is in the balance condition, it is indicating 0 in this. Say, consider this bridge. Okay. There are current I1, I2, I3, I4 flowing in the different branches, and when the galvanometer current is 0, okay, you can say that the bridge is in the balance condition, right? So in this case, if it has say 4 resistive arm which has say resistor P, Q, R and S, okay, and of course this null detector, usually the galvanometer, okay, the bridge is said to be balanced when there is no current flowing through the galvanometer. But because I have just mentioned that this is a null indicator, okay, or null based instrument, okay, we have discussed all this under different analog instrument in our first module. Okay. So expression for balanced Wheatstone bridge can be simply QR is equal to PS, or you can say that P by Q is equal to R by S, right? So we know that under this condition, this Wheatstone bridge is under the balance condition. Okay. So if 3 of the resistances are known, the 4th may be determined from the above equation. Okay. And we can simply calculate the unknown resistor by using S into P by Q. Okay. And if all these 3 are known, R can be easily found. All right. So now in this condition, for the medium resistance measurement, S is known as the standard arm of the bridge, and P and Q, these two are known as ratio arms. And of course, this standard arm is a variable resistor. By tuning this resistor, you achieve the balance condition. Alright. So, this is another way by balancing the resistor for this null indicator. So, this condition you achieve P by Q into equal to R by S in such a way that this galvanometer is showing a 0 current flowing through this. Alright. So, in this kind of conditions, when you have fixed ratio arms, okay, and variable standard arms, the unknown resistor can be obtained. Okay. So, this is the way of measurement of medium resistance with higher accuracy. So, you can have more control over the measurement, as well as the idea is very simple. Okay. So, and also even a small deviation in the resistor value of this R and S may result certain level of current. So, it is till you achieve this 0, you cannot say that this bridge is balanced. Okay. So, it will give you more accurate resistor value. Okay. So, in the next class, we will discuss some more techniques to measure the resistance. We will also talk about measurement of low and high resistances. Thank you.